Precipitates. They are all over your chemistry A level, but what are the colours and formulae that you absolutely need to know from year 1 and year 2 of the course? Let's have a look. So, precipitates. They are absolutely everywhere across the A level, but they start in year 1 and work their way throughout inorganic and physical chemistry to give you this kind of overview of various different tests you can do for cations and anions in aqueous solution. The AS ones centre around the halide ions and then resulting anion tests we can do from those. So the first thing you should remember from GCSE are the silver halide precipitates. These are AgCl, AgBr and AgI. White precipitate, cream precipitate and yellow precipitate respectively. Now those precipitates as well have varying solubilities in ammonia. The AgCl will be soluble in dilute ammonia, the AgBr is only soluble in concentrated ammonia, and the AgI is insoluble. And so even though the colours of them are different, that's a further chemical test you could do to distinguish between each of the AgCl, AgBr and AgI precipitates. What can go wrong when you're testing for them? Well, let's say there were sulfate ions in the beaker first and you didn't know they were there. Now we'll come to the sulfate ion test in a moment, but let's say you hadn't tested for them. And let's say you put in some silver nitrate hoping to find some chloride ions and you get a white precipitate. That might not actually be AgCl. It could be Ag2SO4, which is a white precipitate known as silver sulfate. And silver sulfate would then give you the same kind of result. Silver sulfate is a precipitate you need to know as part of your OCR chemistry A level, and you need to be aware when it can form and where, but why it's there is normally just because the sample hasn't been tested yet for sulfate ions and you are analysing it for halides. So how can you test for sulfate ions? You would use a barium ion solution. Barium ions are Ba2+, so you need to be careful with your formulae, but traditionally you would add something like barium nitrate or barium chloride. Barium chloride is less widely added here because if you were doing a subsequent test later for halide ions, you've just introduced one by adding barium chloride, and so it's not the best idea. Barium nitrate is kind of the go-to one for this, but just make sure that you don't suggest in the exam just adding Ba2+ ions as a reagent, because that's not a reagent. You need to make sure you can suggest something with an intact formulae. So BaCl2 would still be a good bet to go for there. Now, when we actually have barium ions introduced to a solution which contains sulfate ions, you will form BaSO4. And BaSO4 is a white precipitate. And so it's very clear when you perform the test if you've actually got the presence of sulfate ions. But what if you hadn't tested for carbonate ions first? Now, the test for carbonate ions, it doesn't involve a precipitate, can't say the word. The test for carbonate ions does not involve a precipitate, it just involves nitric acid, and then you would get bubbles if carbonate ions were present. But if you don't first remove the carbonate ions from your sample, and you introduce the barium ions, testing for sulfates, you could end up with something called barium carbonate, BaCO3, which looks like a white precipitate, and so would give you the same observation as if you'd got BaSO4. And so you need to make sure that the sample had been tested ahead first. Now, if an exam question says, how do you distinguish between these two different solutions, and one of them's got sulfate ions and one of them's just got like bromide ions in there, you don't need to actively point out first that you're going to remove carbonate ions or something like that to begin with. Now, if you're actually having in an exam to distinguish between two different solutions or two different precipitates, you don't have to worry too much about the sequence that tests need to go into. You just need to suggest a test that would distinguish between those two and allow someone to tell them apart. This needs to normally be a chemical test, not just an observation of, oh, that one already looks a different colour than the other. So you need to be able to perform a procedure for it. What you don't need to worry about with that is the order that the actual steps would go in. You would just suggest something straight off the bat. Otherwise, though, if you were testing one sample for all the different ions that we've just mentioned, so that would be halide ions, carbonate ions and sulfates, you have to do them in a particular order. You have to test for carbonate ions first, using nitric acid, and you'll get bubbles if there are some carbonate ions there. You have to test for sulfate ions second, using barium chloride or barium nitrate, Obviously the barium chloride, you wouldn't suggest that if you would then go into later test for halides, but that's just one of the ones that they will accept sometimes. And then finally, you would test using silver nitrate for the halide ions. Now you have to do them in that order because of the other precipitates that could be formed, barium carbonate and silver sulfate, that I've mentioned already in this video. So make sure you know the sequence matters in one big set of tests, but the sequence doesn't matter when you're just trying to distinguish between two different formulae. It's all about context, and it's knowing when to suggest the right reagent at the right time, in the right order, or when that doesn't matter too much. Now, other precipitates come up in transition metals. Transition metals is part of the upper 6 course, and it sticks out like a sore thumb against all of the other physical and inorganic stuff that you do in preparation for paper 1. Now, for paper 1 then, transition elements is normally quite a big beefy part of that paper because it doesn't look like calculations, and it's this nice wordy or diagram-based set of questions that if you're really good at visualizing structures and precipitates and formulae, you can often do very well with. But there are a lot of precipitates in here that cause problems, and you do have to learn the colours. The systematic names are also important because transition metals are involved. The systematic name is just the traditional naming sequence with the elements and eighths or ides and so on, but often with Roman numerals in, and with the transition elements, it is really important that those Roman numerals are mentioned. For example, copper 2 hydroxide, and that copper 2 needs to be mentioned with the 2 in Roman numerals in brackets. Copper 2 hydroxide is a blue precipitate you need to be aware of. Iron 2 hydroxide is an example of a green precipitate, and again it has those Roman numerals at a 2, telling us that the iron has a 2+ oxidation state. Now iron 3 hydroxide, and this is why the Roman numeral is important, looks very similar if you just write the formula side by side, but that is an orange-brown precipitate, and so you need to know these colours and how the systematic name will help distinguish as well. You've also got manganese 2 hydroxide, which is confusing because in papers, they mention it's a pink precipitate, but then a lot of the textbook resources and so on for OCR say that it's a light brown or a buff precipitate. I'm going to go with pink precipitate only because it's what OCR called it in one of their practice papers. And so whilst I'm sure they would accept both, I have no evidence of this yet, they seem to angle in the direction of calling it a pink precipitate. So I am going to lean on their side of things to play it safe more than anything else. Another one you need to be aware of is chromium 3 hydroxide, which is a green precipitate. Now, all of those different colours of precipitates sound very different, with the exception of iron 2 hydroxide and chromium 3 hydroxide. Those are both green precipitates. So how would we distinguish between those two? Well, it's very similar actually to how we distinguish between different halide, silver halide precipitates. What we need to say is that one of them is going to be soluble and will actually react with excess alkali. The iron 2 hydroxide doesn't. That doesn't react with excess alkali. It maintains a precipitate in the solution. Whereas the chromium 3 hydroxide, if you add excess alkali, so excess sodium hydroxide or very concentrated sodium hydroxide, you'll find that the precipitate dissolves. Please don't say redissolves. A lot of people say that. I don't know why, but it's going to cost you marks. You need to say that the chromium 3 hydroxide will dissolve in excess alkali, and it gives a dark green solution, or you can just say green solution, which is Cr with brackets OH6, and it's also got a 3- charge. So you've got those square brackets around the outside of that. Now that's a complex ion, so that's going to be a precipitate reacting to form a complex ion solution. They often ask for that kind of equation in an exam, so make sure you're aware. I hope that clears up where and when precipitates happen in your chemistry A level. Please make sure that you subscribe to the channel to stay up to date with more from us, because we add stuff all the time to help support your A level, and I want to make sure that you're getting those updates. There's videos all around me at the moment and playlists that you could be watching and making sure that you're getting that A or A star. And if you have any questions, leave them in the comments just down below, and I promise I'll try and get back to you. Until I see you again though, happy revising.